This is SpaceTime, Series 24, Episode 83, for a broadcast on the 21st of July, 2021. Coming up on SpaceTime, discovery of 4 Earth-sized rogue planets all alone in the night, cosmic filaments spinning in space, and China's space program moves into an even higher gear. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study has found tantalising evidence for a mysterious population of free-floating so-called rogue planets, that is, planets which aren't orbiting a host star. The findings, reported in the monthly notices of the Royal Astronomical Society, include 4 planets very similar in mass to the Earth. The discoveries were obtained in 2016 data from the K2 mission of NASA's planet-hunting Kepler Space Telescope. During this 2-month campaign, Kepler monitored a crowded field of millions of stars near the centre of the Milky Way galaxy every 30 minutes in order to spot rare gravitational microlensing events. First predicted by Albert Einstein 85 years ago as a consequence of his general relativity theory, microlensing describes how the light from a background star can temporarily be magnified or lensed by the presence of a foreground star or other object. The authors found 27 short-duration candidate microlensing signals that varied over timescales of an hour to 10 days. Many of these had previously been seen in data obtained simultaneously from the ground. However, the 4 shortest events are new discoveries that are consistent with planets of similar masses to the Earth. And these new events do not show an accompanying longer signal that might be expected from a host star, suggesting that these new events could be free-floating planets. It's thought such planets would have originally formed around a host star, but were then ejected into interstellar space through gravitational perturbations during interactions with other planets in the system. The study's lead author, Ian MacDonald from the University of Manchester, says that roughly 1 out of every million stars in our galaxy is visibly affected by microlensing events at any given time. But only a few percent of these are expected to be caused by planets. The fact that these planets were found at all is quite an achievement. See, Kepler was never designed to find planets using microlensing techniques, nor to study the extremely dense star fields of the inner galaxy. This meant that new data reduction techniques had to be developed in order to look for signals within the Kepler database. Confirming the existence and nature of free-floating or rogue planets will be a major focus for NASA's upcoming Nancy Grace Roman Space Telescope as well as ESA's Euclid mission, both of which will be optimized to look for microlensing signals. This is SpaceTime. Still to come, cosmic filaments found spinning through space, and China's space program moves into an even higher gear. All that and more still to come on SpaceTime. A new study has found that galactic filaments, which make up the cosmic web-like structure of the universe, are actually spinning in space. The filaments are composed of galaxies and galaxy clusters, forming tendrils hundreds of millions of light years across, which interconnect the larger nodes of galactic superclusters. The new findings, reported in the journal Nature Astronomy, are based on maps of the motions of galaxies using the Sloan Digital All-Sky Survey. The authors examined the velocity of galaxies perpendicular to the filament's axis by measuring their Doppler shift with a spectrometer, finding that they were displaying motion consistent with rotation. In other words, the part of the galaxy moving away from us would look red, while the other part of the galaxy, that moving towards us as it rotates, would look blue. The study's lead author, Noam Libeskind, from the Leibniz Institute for Astrophysique in Potsdam and the University of Lyon, says the observations showed that these are the largest known objects in the universe to have angular momentum. Libeskind says they're moving on helixes or corkscrew-like orbits, circling around the middle of the filament while travelling along its length. He says this kind of spin has never been seen before on such enormous scales, and speculates that there must be an as yet unknown physical mechanism responsible for these talking events. To find out more, Andrew Dunkley is speaking with astronomer Professor Fred Watson.
It's another major announcement / discovery. They've been mapping the motions of galaxies. Now, we're talking a massive scale here. This isn't just sort of looking at us and Andromeda and those other tiny little unfortunate galaxies that we're eating at the moment. We are talking massive super galaxy clusters and how they're all linked and how they're all rotating. They have now basically confirmed that there's this big movement going on a colossal scale, and I love that word. And now, and this is so typical of astronomy. They've made the discovery, they've announced it, but they don't know why.
Yeah, that's right.
Am I right? I mean, is that what we're talking about?
To step back from the news, just to remind people of what the big picture is. When we look deep into the universe, okay, we see galaxies, of course, as you mentioned. We also see clusters of galaxies. There's a very big one nearby, the Coma cluster. And these are sometimes thousands of galaxies. But when you really start looking at the big picture, and you're probing now to usually quite significant distances in the universe before you can see this picture emerging, I'm happy to say I've been on the periphery of being involved with this kind of work. Actually, not that much on the periphery, because I built the instrument that did some of it.
Cool.
Back in the 1990s and 2000s. And it comes, our knowledge of this phenomenon comes from what we call galaxy surveys, where you basically map in three-dimensional space where galaxies are over as big an area of the sky as you can. And in fact, we did it for the whole of the southern sky with something called the 60F Galaxy Survey, which I was project manager for back in the early 2000s. But there are other surveys that have been done with similar technology. We do it all with fiber optics, and I have time to talk about that. But that was what I helped to sort of pioneer back in the early 1980s. There was a group of us throughout the world who tinkered around with these fiber optics, knowing that the end product could be measurements of galaxies thousands at a time, and now they're hundreds of thousands at a time and millions at a time with similar kind of technology. So when you do that, when you look at these maps of galaxies, you find this structure within it, which we call the cosmic web. And it is reminiscent of, walking into a room that's not been cleaned for decades and finding the whole place.
You're not looking behind me, are you? I mean,
well, that's where I got the inspiration from, Andrew. There's this web. It's also like a kind of honeycomb. It's not perfectly hexagonal, but it's strings of galaxies stretched over colossal distances with great voids in between them where there aren't any galaxies. That's called the cosmic web. The voids, the honeycomb cells, if you want to use that analogy, are typically hundreds of millions of light years across. They're enormous. This is a structure on the grandest scale, and we think it's actually the result of the way matter behaved in the immediate aftermath of the Big Bang. You can see the seeds of it in the cosmic microwave background radiation, where we're looking back to a time before the first galaxies formed. But there is structure in the temperature of the cosmic microwave background radiation, which suggests that what you're going to get when you get matter forming stars and planets and galaxies, you're going to get this web-like structure. So the structure is well established. But what has happened now is that people have looked in detail at what we call the filaments, the sort of cobwebby stuff that joins the scaffolding, let me put it that way, of the cosmic web. And basically, these filaments link together gigantic clusters of galaxies, which are at what you might call the nodes, the places where things cross, the corners of the hexagon, if you think of it as a honeycomb. So looking in detail at that, and this is scientists from AIP, an institution I know very well because I've worked closely with them, the Leibniz Institute for Astrophysics in Potsdam. They've worked with scientists in China and Estonia. And what they've discovered is that these filaments, long tendrils of galaxies, they actually spin. And that is a brand new discovery. And it's a record breaker in the sense that we've never seen rotation on such a vast scale before. We see rotation in pretty well everything in the universe, but a rotation of the filaments of galaxies. And remember, these are made of galaxies which are themselves significantly separated. They're actually rotating. So that's a new discovery and quite a surprising one. Although I have to say, I was interested to see that theoretical astronomers, these are the people who work out the models of what the universe looks like, they've suggested that these things should spin and sent people off looking for them, which is why the scientists at the Leibniz Institute have discovered them, the spin of the filaments in the cosmic web. How did they measure it? Well, by the same way that we always measure rotations, which is using the Doppler effect. The fact that light from an object moving towards you is shifted towards the blue in the spectrum, light coming from an object moving away from you is shifted towards the red, hence the term redshift, although that is nuanced slightly differently, but on the scale of the universe. But it's the Doppler effect. That's what's allowed the scientists to work out the galaxies on one side are coming towards us, in effect, despite the fact that they're all moving away because of the expansion of the universe, but they're more coming towards us than the ones on the other side, which are more going away from us. So that's how the rotation has been detected. And exactly as you've said, even though this is predicted, it's a struggle to understand why the rotation should be there. It's another aspect of it, just one final thing before I let you get a word in edgeways. The galaxies themselves actually move along these filaments. The filaments are made of galaxies. So what you've got is this, imagine an individual galaxy. It's moving like a corkscrew. So it's moving along the galaxy and it'll wind up in a big cluster of galaxies at the corner between your tendril and the next one. But they're moving along in this spiral orbits, basically, along as well as rotating. So the whole thing is, this whole filament is rotating as the galaxies move along it. And it's up to you to work out why that is happening, Andrew.
Yeah, I've got my pen here. And
yeah, good. I should mention pens because a pen is or a pencil is a good analog for the overall shape of these things. They're that long and that thick, but scaled up to millions of light years.
And are they sort of spinning on an axis while everything inside's rotating, or we've got multiple movements happening at once?
They may well be, but that would be a much smaller. It's spinning around the line of the pencil.
Okay.
If you imagine a pencil being twisted, that's what's happening.
Right. Wow. And of course, that opens up the big question as to why and
Indeed.
How it all started, and it could go back to as far as we know back. You don't know.
There's another line you could take with this. So the reason why planets revolve around their parent stars is because planets and stars are formed from clouds of gas and dust. And those clouds are ginormous. They're much bigger than the solar systems that they form because they often form many, many solar systems within them. Gas and dust is a fluid, and so they've probably got little eddies within them. And it's those eddies that lead to the rotation of planetary systems and stars. Because if you've got something that's collapsing under its own gravity and it's got a little tiny set of eddies in it, there'll always be one eddy that's more strong than another one. So that becomes the preferred direction of rotation. And as it collapses, that rotation is locked in ever more solidly by something called the conservation of angular momentum. And so things rotate faster. And that's how you've got, a flat protoplanetary disk in young solar systems and the planets forming in a plane. Now, the thinking regarding the cosmic web is that there is no overall rotation of the universe, but there might be sort of eddies of rotation within the material of the early universe that could have given rise to a similar process, a rotation of these tendrils. I'm not making that very clear, but it's probably the rotation is probably a fossil of general eddy rotation within that bit of the primordial fireball when the universe was created.
Do we know how fast this rotation is, or they haven't figured that out?
I looked for that. I think it's in the original paper, which I didn't have a chance to look back at. But it's clearly not once a day or anything like that.
Yeah.
It's probably spinning on the scale of many tens of, if not hundreds of millions of years for one rotation.
Wow, extraordinary. Well, hopefully one day they'll get more answers to this one. It might answer other questions if they figure it out. That's right. Quite amazing.
And of course, it's all intimately linked, Andrew, with dark matter, because we think that dark matter is the reason why this cosmic web forms the way it does. Dark matter is one of the principal agents of gravitation. That's right.
That's Dr. Fred Watson, an astronomer with the Department of Science, speaking with Andrew Dunkley on our sister program, Space Nuts. And this is Space Time. Still to come, China's space program moves into an even higher gear. And later in the science report, the Earth's upper atmosphere is contracting due to increasing greenhouse gas emissions. All that and more still to come on Space Time. China has ramped up its launch campaign even further as Beijing continues its build-up to war with no less than 3 orbital missions in 4 days. These have included a Long March 3C rocket, launched from the Xichang Satellite Launch Center in Sichuan Province. The mission carried the Tianlin 105 data tracking and relay communications satellite for the Chinese military into a 36,000-kilometre high geosynchronous orbit. Just hours later, a Long March 4C rocket was launched from the Zhuquan Satellite Launch Center in northwestern China, carrying the Fengyong 3E meteorological satellite. The spacecraft, which is equipped with 11 remote sensing payloads, was placed into an 800-kilometre high polar orbit. And then, to round off an incredibly busy week, a Long March 6 rocket was launched from the Taiyuan Satellite Launch Center in northern China's Jiangxi province. It was carrying 5 new-generation Ninja-1 signals intelligence gathering satellites, which were placed into an 860-kilometre high orbit. The US Space Command says China now has more than 400 satellites in orbit, second only in number to the United States, and is expected to have at least 1,000 satellites flying around the Earth by the end of this decade. By comparison, back in 2010, Beijing had just 70 satellites in orbit. The majority of Chinese spacecraft are devoted to space-based intelligence, surveillance and reconnaissance gathering missions, closely followed by its Beidou satellite navigation satellite constellations and then its communication satellite systems. Combined, these capabilities provide Beijing's military with a global command and control ability. This is SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with a science report. A new study has shown that symptomatic COVID-19 patients can take an average of 80 days to return to a normal heart rate. A report in the Journal of the American Medical Association looked at some 900 people who reported symptoms of an acute respiratory illness. They found that around a quarter tested positive for COVID-19. They were fitted with wearable technology tracking their heart rate, sleep and step count. Scientists found that those with COVID-19 took longer to return to a normal resting heart rate, normal sleep patterns, and normal amounts of exercise compared to those with other respiratory illnesses. The authors found that COVID-19 patients took about a month on average to return to normal sleep and exercise, but took an average of 79 days to return to a baseline heart rate. The World Health Organization now estimates more than 8 million people have been killed by the COVID-19 coronavirus, with more than 4.1 million confirmed fatalities and some 190 million people infected since the deadly disease first spread out of Wuhan, China. A new study has confirmed that parts of the Earth's upper atmosphere are gradually contracting in response to increasing levels of man-made greenhouse gas emissions. Scientists combined data from 3 NASA satellites to develop a long-term record which reveals that the mesosphere, that's the layer of atmosphere between 50 and 80 kilometres above the surface, is cooling and contracting. Researchers have long predicted this effect of human-driven climate change, but it's been difficult to observe the trends over time. The findings, reported in the Journal of Atmospheric and Solar Terrestrial Physics, is based on 30 years of satellite observations by NASA, and showed that the summer mesosphere over the Earth's poles is cooling by around 8 degrees Celsius and contracting by around 150 to 200 metres every decade. The upper boundary of the mesosphere is where the neutral atmosphere begins transitioning into the tenuous electrically charged gases of the ionosphere. Even higher up, around 240 kilometres above the Earth's surface, the air causes what's known as atmospheric drag, the friction which causes satellite orbits to decay, but also helps clear space junk. So, as the mesosphere contracts, more and more space junk will be left in low Earth orbit. Scientists using the world's largest atom smasher, the Large Hadron Collider at CERN, have successfully measured lepton flavor universality, a fundamental principle of the Standard Model of particle physics. The findings, reported in the journal Nature, support the fundamental foundation stone upon which our understanding of the universe is based. Leptons are one of the building blocks of the universe, and they come in several types known as flavors. These include electrons, muons, and taus. Scientists tested the attractive force between muons or tau leptons and another type of fundamental particle called a W boson, a force particle. They found the attractive forces were the same for both types of leptons, which is known as the lepton flavor universality, thereby confirming a key assumption of the Standard Model. Israel has used a high-powered airborne laser to shoot down drones in a series of tests. The IDF says the new system can target and down any flying object, including drones, mortars, rockets, and ballistic missiles out to a range of 20 kilometers. The system uses Israel's existing aerial defense technologies to track and lock onto a target before firing a 100-kilowatt laser beam, which burns through the target. The IDF is now also developing a parallel ground-based laser defense system for aerial threats. The lasers will be used alongside Israel's existing short-range Iron Dome missile defense system, as well as its medium-range David Sling missile system and its high-altitude Arrow missile interception systems. The growing urgency for these anti-missile systems follows attacks by Hamas terrorists over recent months, which saw over 4,300 missiles fired against Israeli civilians. Well, it seems Microsoft's print nightmare computer vulnerability has been somewhat of a nightmare to fix, and worse still, it's not fully resolved yet. With the details, we're joined by technology editor Alex Zaharov-Reut from ITWire.com.
The print nightmare vulnerability allowed remote hackers to break into server, business, and consumer Windows computers. But there's a catch that Microsoft will undoubtedly have to fix in a future update. The Windows Update server should have updated your computer by now, and Windows 7, 8, 8.1, and Windows 10 computers are affected. I think other earlier versions of Windows are affected as well, but they've long ago lost their support. And if you are still using those computers, you should use them offline only. But interestingly, Windows 7, because Microsoft knows there's still 30 or 40% of the Windows users out there still using Windows 7, this has received a patch as well. And it stops the remote ability for hackers to break into your computer and use the vulnerability in the print spooler to then install software onto your computer. So the patch does stop that. But if you have a hacker who's in front of your computer or in your network somehow, physically there, they could still use this vulnerability to break in, which has been reported by a number of online news organizations. But the reality is that if a hacker is right in front of your computer or in the building, it's very difficult to stop them from being able to use other means to break in. So it's not the end of the world that hasn't been patched yet. Microsoft will patch that. But people who use Zebra printers, which is often used in retail and industrial settings, apparently the Zebra printers stopped working. If you tried to reinstall the Zebra printer, you had to do so in admin mode. You had to be logged in as an administrator, which is not always the case for industrial computers. And the other way of getting Zebra printers to work was to roll back the update, but of course that's not recommended. It just shows how complicated security is in 2021 and all the crazy ways that hackers look for places to break into computers. Who would have thought that the print spooler, the thing that talks to your printer and sends it the information, would be a way to break in? But give hackers a challenge and they'll meet it.
When I was a kid, I looked with envy at the Tag Heuer watch, and I didn't mind playing Nintendo occasionally. And now these two dreams of my childhood have combined.
Yes, well, Nintendo has been in the watch business for a long time. If you think about the fact that they had the Game & Watch, it wasn't really a watch. It was the handheld console, which has, of course, grown into the Nintendo Switch that we know and love today. But yeah, Tag Heuer has announced a long-term collaboration with Nintendo, which probably means a whole series of other watches are yet to come. But they've announced 2,000 limited edition Super Mario Tag Heuer connected watches at a cost of a reported US $2,150. They run the Android Wear OS, so they're proper smartwatches, and they'll do all the various things that smartwatches do for fitness, running different apps. But they now have a special series of Mario watch faces, so you can see Mario in various poses. There's a video online that you can see. You can see Mario growing. You can see him jumping out of one of those tunnels. You can see the star and the mushroom and even Mario swirling around the pole. The watch itself has lacquered sort of an M symbol on the crown, and it's got a red case, travel case, and it's got these little sort of touches. They sort of want to gamify the Mario experience. I mean, there's no actual Mario game on the watch, which is a shame. It would have been fun if you could sort of have played Super Mario on your watch, but it would be.
That's what I thought was going to happen.
Well, the problem is that it's only sort of an inch big. I mean, it's not a very large space, so it's more like a statement. It's a way to show off that you have the ability to buy a Tag Heuer.
Flying car too, by the way. That hasn't
right.
come yet.
Yeah. Look, I'm sure somebody will come up with some sort of Mario game. I mean, on your iPhone, you can get a Mario Runner type game.
Yeah.
So there is Mario on iPhone and Android. But really, if you want the true Mario experience, and Nintendo wants you to buy a Switch or one of its previous consoles, I mean, you can still buy those little Game & Watch devices for very expensive amounts of money on eBay, and probably people have them sitting in their garages or in their kids' bedrooms. It could be worth some money. But anyway, if you are an existing Tag Heuer connected owner and you're thinking, damn, I want those watch faces, well, they will come to you later this year. But at the moment, of course, they're keeping it as an exclusive for people to buy one of these 2,000 limited edition watches. And then we'll have to see what else Tag Heuer and Nintendo collaborate on in the months and years to come.
That's Alex Zaharov-Reutt from ity.com. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.